The basic concepts of local extrema in R3, local max min, and now also saddle, are, I think, pretty straightforward. But I need to calculate these things. I need some sort of a test. What do we use in Calc 3 that is the analog of a number line of f prime, increasing, decreasing? In Calc 1, the answer is the second derivative test. So I want some sort of test or method for finding local max min as well as saddle points for a function f of x, y. And the name of this is the second derivative test. I won't go through the proof, although it's pretty fantastic. Here I'll just roll out the machinery. This is another small item that I recommend committing to memory. Begin with a point. A, B. We already know how to test 4 critical points, so let AB be a critical point for the function f of x, y. So, i.e., the gradient of f of x, y is the 0 vector, which is the same thing as fx is 0, and fy, well, it's really fx at a and fy at b is 0. So this really should be f gradient evaluated at ab, and likewise, this should be fx at a is 0, and fy at b is 0. All right, now introduce a new function called the d function, capital D. Let capital D, which is a function of a and b, be equal to fxx, second with respect to x, of ab times fyy of ab minus fxy of ab squared. If you want to know where this comes from, it's really a determinant in the same form of the 2x2 determinants we did long ago. It's the determinants of a really special matrix, namely a matrix that has components fxx, fxy, fyx, and fyy. The reason, of course, I can just square it is that fxy is fyx. All right, then we get the following. For separate and wonderfully memorizable cases. Set it up like this. So, first D evaluated at AB, fxx evaluated at AB, and the result. All right. The first possible case is this d function will be positive and fxx will be positive, in which case you've got a local min. Memorize this however you like. Why 2 positives make a min, 2 rights make a wrong? I'm not sure. B, again, d has to be positive here. fxx is negative, in which case you've got a local max. C is if this d function is negative, in which case it doesn't matter what fxx is. It can be anything you like. The result is C, this Gets me the saddle. Finally, this test breaks for the case where this thing or discriminant equals 0. This tells me I have to go looking elsewhere. Don't worry, this class is not about trying to fool you with these really weird pathological cases. This is what you want to hold on to. I didn't have room to squeeze it in here, but of course I mean when I say local min, I mean a local min or max at the critical point AB, and as usual, please make sure to distinguish between where it is, AB, and what it is, F of AB. So the where is AB. The what is F of AB, the actual value. So the what or the value is F of AB. Let's take this out for a spin. Return to the first example we did. F of xy is x squared plus 2, or actually plus y squared minus 2x plus 6y, and I think it was plus 14, yeah. All right, find the local extrema. To do so, begin with critical points. So, critical points, fx is 2x minus 2, which will be 0 precisely when x is 1, and fy is 2y plus 6, which is 0 precisely when y is minus 3. I, of course, did this already, but in any case, critical point 1 minus 3. All right. What is fxx? I want to build that d function for the second derivative test. Fxx is 2. Fxy is, I can take fx and differentiate it with respect to y, or I can take fy and differentiate it with respect to x. Namely, if I differentiate fx with respect to y, I get 0. Fy with respect to x, I get 0. It should be the same by Clause's theorem, so I get 0 there, and fyy is fy with respect to y, or 2. That tells me that d of any point AB will be fxx, AB fyy, AB minus quantity fxy, AB squared. However, AB plays no role in any of this because fxx is always 2, fyy is always 2, and fxy is always 0. So I wind up with the d function is 4, which quite clearly is positive. That means, according to the second derivative test I had a moment ago, that I'm going to have a local max or a local min depending on the sign of fx at AB. So, or the critical point, fx at 1 minus 3 will be, let's see, 2 times 1, which is, hang on a moment, excuse me, fxx at AB. Not fx at AB. fxx at AB, after all, it's called the second derivative test. I should be using second derivative of 1 minus 3. Again, this is always 2, which is positive. So I have a positive fxx with a positive d. So that tells me I've got a local minimum. Specifically, f has a local minimum at 1 minus 3, and the minimum value is f of 1 minus 3, which when I plug in here gets me 4. This is pure coincidence, the fact that the second derivative yielded 4 and the value of the function is 4. All right, not too difficult. At least I know that what should be true is true. Let's see what else. Consider, say, fxy is y squared minus x squared. Will the second derivative test bear out what it's supposed to? First order of business, critical points. So, critical points, fx will be minus 2x, fy will be a positive 2y. Both of these are 0 when both x and y are 0. So I've got, once again, critical point 0, 0. Roll out the second derivative test. fxx is minus 2, again independent of whatever x and y are. Similarly, fyy is positive 2, and if I differentiate x with respect to y, or sorry, differentiate fx with respect to y, or fy with respect to x, I get 0. So I get that d of any point, ab, will be fxx, ab, fyy, ab, minus fxy, ab, quantity squared. But again, the ab makes no difference here. These are awfully simple examples. This is a minus 2, this is a 2, this is a minus 0 squared. So in this case, d of any point, let alone the critical point 0, 0, will be minus 4, which quite clearly is less than 0. So, fantastically, I get what I should from the graph. I have that f of 0, or I should say f has a saddle at 0, 0. So f has a saddle point, and it has it at not just 0, 0, but might as well put in the z coordinate as well. F of 0, 0, which, by the way, is also 0, n. So, saddle point at 0, 0. So it works for the ones we computed by definition. Find and classify the local extrema for the function f of xy is x to the fourth plus y to the fourth minus 4xy plus 1. All right. This same idea, a bit more complex of a function, but let's start with critical values. Sorry, critical points. Fx will be 4x cubed minus 4y. Aha, more complex already. And Fy will be 4y cubed minus 4x. All right, so if both fx and fy are 0, fx is 0, tells me that, well, x cubed minus y is equal to 0. This, by the way, says y is equal to x cubed. I'll use this first equation together with this second to get the critical values. So already the algebra is a bit more interesting. By the way, you could have started with the other one and plugged it into the first. Namely, you could have solved fy for a relationship of x and y's and plugged it into fx instead of what I'm doing here, namely fx into fy. So this is 0, fy that is, tells me that y cubed minus x is equal to 0, but I have y is equal to x cubed. Namely, this will be x cubed quantity cubed. This is a Price, not Zhang approach, technically. All right, this gets me x to the 9 minus x equals 0, which requires a bit of factoring and maybe even more colors. This will be, well, x times x to the 8th minus 1 is 0. This factors as x to the 4th plus 1, x to the 4th minus 1 is 0, but that x to the 4th minus 1 also factors. I get x to the 4th plus 1, x squared plus 1, x squared minus 1 is 0. This factors once more. I'll just hang out down here at the bottom of the board. To x to the 4th plus 1, x squared plus 1, and then the x squared minus 1 factors to an x plus 1, x minus 1 is 0. Just algebra. Because x to the 4th plus 1 and x squared plus 1 don't factor, so this gets me x is 0 and plus or minus 1. Super. What are the y values that correspond to this? If I plug, let's see, this back into, let's see, when x is 0, I get y is 0. When x is 1, I get y is 1. When x is minus 1, I get y is minus 1. So I've got critical points 0, 0, 1, 1, and minus 1. Minus 1. Where did I get this? Once more, I'll use, say for example, right here, when x is 0, I get y is 0 cubed is 0. And when x is minus 1, I get y is minus 1 cubed is minus 1. And when x is 1, y is 1 cubed is 1. So, get these, put them back in there. Got my critical points. All right. The second derivative test. So, see, I need fxx, fyy, and fxy. And I'm a bit short on space, so I'll compute them right here since I've got my fx's and my fy's. fxx will be 12x squared. Fyy will be 12y squared. And fxy, again, I can differentiate fx with respect to y or fy with respect to x. In both cases, I get a minus 4. All right, so I now need to see what I get using second derivative test for each of these critical values. Namely, if I begin with critical point, my d of the critical point AB, and fxx of the critical point AB. All right, critical point 0, 0. Well, that will get me, let's see, 12 times 0 squared times 12 times 0 squared. This is fxx of 0, 0, fyy of 0, 0, and then minus a minus 4 squared. That turns out to be a minus, let's see, do I agree? Yes, a minus 16, which quite clearly is less than 0, which is all I need. That will be saddle. Let me squeeze once more this function I'm using here. Remember, d is fxx, fyy minus fxy squared evaluated at the appropriate critical point. All right, 1, 1. For 1, 1, I'll have 12 times 1 squared. That's fxx at 1 times 12 times 1 squared again. That's fyy at 1 minus, and once more, a minus 4 squared. So it's 144 minus 16. It's some number that I'm pretty sure is bigger than 0. So I need to find fxx of 1, 1 as well to see if I've got max or min. fxx of 1, 1 is 12, which is positive. So I got a max. A min. Minus 1 is going to work out almost identically. 12 minus 1 squared times 12 minus 1 squared minus 4 squared. This is, again, the number that is equal to 144 minus 16. All I care is that it's positive. Meanwhile, fxx of minus 1 is, again, 12 times minus 1, or I should make this 12 times 1 squared. This will be 12 times minus 1 squared, which is, again, positive. So I've got a saddle here and 2 local mins. Namely, this tells me saddle at 0, 0 and f of 0, 0, which will be 0, 0, 1. Saddle. What about 1, 1? At 1, 1, I've got 1, 1, f of 1, 1. F of 1, 1 will be 1 plus 1 minus 4 plus 1, which is a minus 3. So I've got local min at 1, 1. 1, 1, 1 minus 4, so minus 1. And here, again, I've got a local min, namely at minus 1, f of minus 1, which will be minus 1, minus 1. So minus 1 to the 4th is a 1. This will be again a negative 4 and again a 1. So this is again a minus 1. Local min. So in pink, I've got my classified critical values, namely saddle at 0, 0, 1. Then local mins at 1, 1, minus 1, and minus 1, minus 1, minus 1. See if I can squeeze a graph of this thing here. No, not you. This color. So it should look like this. And if I remember, it's almost like a set of trousers. Here is the, there we are, the legs sort of come down that way. Here is the saddle at 0, 0, 1. So this is actually the trousers that ride the saddle. So I'll begin my z-axis there and call that the point 1. And then I move it ever so slightly up, then I've got y-axis there, x-axis there, and I'll have here, this will be 1, 1, minus 1. This will be minus 1, minus 1, minus 1. And then here at the saddle, 0, 0, 1. I now want to begin to apply max and min for functions of two variables to situations other than just the graphs directly. So, for example, find the shortest distance from a point 1, 0, minus 2 to a plane. X plus 2y plus z is equal to 4. Distance minimization problems are awfully common for Calc 3 optimization, especially because we can move around in R3 quite nicely. So what is it I'm looking to minimize? What do I want? I want to minimize distance. Want to minimize the distance from the point to the plane. There's a function for such minimization. Namely, I'm looking to minimize the distance formula, which is the square root of x minus 1 squared plus y minus 0 squared, so just a y squared, plus z plus 2 squared. So I'm minimizing distance from a point. So this is distance from the point 1, 0, minus 2. However, the point must also lie on the plane x plus 2y plus z, where x plus 2y plus z is equal to 4. This is the same thing as saying z is equal to 4 minus x minus 2y. So I'm looking to minimize distance from a point, and the phrasing here is very exact, subject to this additional condition. I'm going to bring that right into the next and final section for the class. So that means that I want to minimize the function d is equal to this square root of x minus 1 squared plus y squared, but the z can be called 4 minus x minus 2y. And so this is a plus 4 minus x minus 2y, and then plus a 2. Quantity squared, which of course is the same thing as x minus 1 squared plus y squared plus 4, nope, that'll be a 6 after I add it. 6 minus x minus 2y squared. That means this is the function I'm interested in minimizing. It's quite clearly a function, little d of x and y. That square root's rather gnarly, so actually suffices, or easier, to minimize, say, f of xy, which will be d of xy squared, namely everything without the square root. X minus 1 squared plus y squared plus 6 minus x minus 2y squared. All right, the reason I can do this is because clearly the square root is minimized when the square is minimized. This is a bit of a trick. All right, I can begin to play second derivative test. First, I need another color. And I need to find my partials with respect to x and y in order to find my critical points. Fx, this is going to require a small amount of chain, 2x minus 1, and then I lose everything with a y, and then plus a 2, 6 minus x minus 2y, times minus 1. This will clean up to be 4x plus 4y minus 11, which equals 0 precisely when, 4x. No, that's right. 4x plus 4y minus 11 equals 0. Hold on to that just a second. And Fy, on the other hand, will be 2y, then plus a 2 times 6 minus x minus 2y, and then chain gets me another minus 2. This then becomes 4x plus 10y plus 24 is 0. And yeah, if I trust my writing, which I did before, so it's a bit more trustable, I get critical point. X will be 11/6 and y will be 5/3. So I now need to see, do I get a minimum? Let's see, fx, x, fyy, and fyz. So fxx, I can differentiate this x, again with respect to x, gets me a 4. Fyy, here with respect to y, gets me a 10. And fxy, I'll differentiate this guy with respect to y. I think that also gets me a 4. And these, by the way, are entirely independent of any x or y values. So my d function of any xy will be fxx fyy, 4 times 10 minus fxy squared, which is then minus 16. It's again some number which is positive. I need then to know what happens for fxx evaluated at 11/6 and 5/3. Well, fxy is always 4. So this tells me fxy at 11/6, 5/3 is also 4, which is positive. And I guess here I should have technically said I'm plugging in 11/6 and 5/3. Not that it makes much difference, because d is always 4. But it's nice to emphasize that the formula calls for the points to be plugged in. So here, really, I plugged in x is 11/6 and y is 5/3. So I've got that the function f of xy has a minimum at 11/6 and 5/3. But this doesn't answer the question entirely, because I'm asked to find the shortest distance, so I don't just need the function, or where the function is minimized, I need what the function value is when it's minimized. Let's see then, f of 11/6 5/3 will get me, just by staring at it or my notes, 25/6, which is probably an answer in the multiple choice version of this world, and it's a wrong answer. Why? Because I needed a critical value that minimized f. And the reason I was looking to minimize f is that f is minimized where d, the original guy I was seeking to minimize, is minimized. They have the same critical points and they both have min and max in the same place. F, though, is a squared version of d. That is the square of the distance. So the shortest distance is d of 11/6 5/3, or the square root of 25/6, or I don't know, 5/√6. This is true, it's just not the answer to the question. Notice finally that we're beginning to double back on ourselves. It's actually a 12.5 question. You can find this straight up using distance formula from the point to a plane. I think that's how we concluded that long section. And there'll be yet another way, a third way, of actually minimizing the distance. So theory begins to ties into itself. Finally, I want to talk about absolute max and min in R3. As usual, I want to take what's true in Calc 1 and see if we can scale it up to Calc 3. So, what is true for absolute extrema in Calc 1? Namely, to find an absolute max or min of a function f of x, and it is important that we look for the absolute on a closed interval. Weird things happen when it's not. You maybe played with that in Calc 1. Here, for functions of two variables in Calc 3, we just want the nice case. Nice case is when you have a closed region, in this case a closed interval. Alright, so to find the absolute max min of a function on that interval, you need two things, or to do two things. One, evaluate f on the critical values, but not just all critical values. You need to evaluate f on the critical values that lie in the interval AB. As in the example I did for absolute extrema at the beginning of the section, there was a min that lied outside the interval and therefore is not counted when looking for absolute. Two then, evaluate f on, and I'm going to call it the boundary of the interval AB. Eventually, once we generalize, it's no longer just the endpoints of the interval, it's the boundary of a region. In this case, the boundary of this is equal to the nice special case of endpoints A and B. In this case, then, the maximum, or the absolute max, is the max of whatever you got in 1 and 2, and the absolute min is the minimum of whatever you got in 1 or 2. Alright, let's move this now to Calc 3. Once again, 1 and 2 account for the fact that the critical values must lie in the interval. So, this is going to be similar in spirit, but a bit different in practice. So here I want to find the absolute max min of a function, but here it's of a function f of xy, and it's not on an interval, it's on a region D that lies, this is the symbol for subset, inside of R2. So AB was a subset of R, here D, this means subset of R2. And again, here I'll assume, just to make life easy, that the subset is closed. All right, so it will look, again, similar in spirit, but a bit different in practice. The first step will be to evaluate f on critical values. So, again, evaluate f on, or now it's at the critical points. So evaluate f at the critical points, which as usual you find by setting fx equal to 0 and fy is equal to 0. 2, I now need to evaluate f again on, and this is why I chose the word boundary, because the boundary of a region in R2 is very different than the boundary of a subset of R1. So if here's your real number line and here's your interval AB, then the boundary is simply the endpoints A and B. Boundary of the interval AB is just the endpoints A and B. However, consider now a region D inside the xy plane that lies underneath a function. So this, for example, region D here into the xy plane, which when just graphed as part of the domain looks like that. Its boundary is not 2 points, it's not 4 points. It's again the phenomenon we've come across when moving our domain from R to R2. It's got infinitely many points. Namely, evaluating the boundary here, in this case, will mean evaluating everything here, 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 and here. The pink part that is not on the inside. So the outside box in this case. And by no means will we just be restricted to a box. You can have, say, a boundary that doesn't just look like that, but say first in R3, it can look like this, and that's supposed to lie in the xy plane, and when you move it to the domain, it looks like that. Evaluating on the boundary now becomes a significantly more complicated affair. Same principle, but the second step significantly more difficult. A final word about this second step. It can really be done, well, in several ways, but we'll concern ourselves with 2 of them. One will be to do a Calc 1 analysis on the boundary. on the boundary. And you'll see what I mean in the next example. The other is going to be covered in the final section, which is the next section of this book, the final section of the class. This will be done, I think it's 14.8. It'll be an instance of what are known as Lagrange multipliers. And here I should say use Lagrange multipliers since they have many other uses. Find the absolute max and absolute min of the function f of xy is x squared minus 2xy plus 2y on the rectangle, which is the region D, and it's described theoretically as the set of x, y, where x is between 0 and 3 and y between 0 and 2. Okay, so step 1 is to find the critical values and evaluate f there. So, 1, the critical points, that is. Let's see, fx is 2x minus 2y, which equals 0, precisely when 2x minus 2y is 0, or x is equal to y. Fy is going to be, let's see, that's a 0 minus a 2x, and then minus a 2. So, Fy, where am I? There I am. Minus 2x, and then, sorry, minus 2x plus 2. This is 0, of course, precisely when x is 1, which implies, since x equals y, that y must also be 1. So I've got critical point, nice and pretty, 1, 1. I don't need to determine whether this is a min or a max, because I'm not looking for a local extrema. I need absolute extrema. It may also be interesting, but that's not what the question asks. So, evaluate f at the single critical point. 1, 1, I get 1 squared minus 2 times 1 times 1 plus 2 times 1, brilliant, equals 1. All right, so the point here is 1, 1, 1. All right, now I need to play boundary. The region D lies in the xy plane as a box. It's a box where x is between 0 and 3 and y is between 0 and 2. So here is the region enclosed by precisely this box. Said differently, the region D has boundary, the box, made up of 4 lines, which I'll label, let's see, L1, match the book, that's L1, L2, L3, and L4. All right. This is a bit of what I meant before, or just a moment ago, when I said I need to do some Calc 1 analysis on this surrounding box. So the region D has boundary, the box made up of L1 and L2 and L3 and L4. I need to analyze the behavior of this function f of xy on each of these L's. So let's start. L1. In L1, I'm on the x-axis, so y is 0. Said differently, y is 0 and x ranges between 0 and 3. When I'm on L1 and y is 0, it says that my function f of xy becomes f of 0, or sorry, x3, f of x0. Again, a similar analysis is the one we did when playing with limits, because I'm traveling on the x-axis, y is always equal to 0, so this thing is going to be a simple x squared, because it zeroes out all the terms with y's. So I've got a function increasing in x, f of xy equals x squared on L1, which is increasing from 0 to 3. So that says I'll have a minimum at f of 0, 0 equals 0, and a maximum at f of 3, 0 equals 9. Let me box these as I go along, because this is just one set of min and max on the line L1. I need L2, 3, and 4, and I'm going to fit it on this board. How will I do it? All right, I put L2 there. All right, L2, y varies, but x is fixed at 3. Namely, f of xy will be f of 3y, because x is fixed at 3 and y varies. So if I throw 3 into y, 3 into x, and I leave y alone, I get 9 minus 6. Agree? Yes, minus 6y plus 2y. Yes, yes, yes. So 9 minus 6y plus 2y, which is 9 minus 4y. All right, another small bit of calc analysis. This is a decreasing function when y is between 0 and 2. So that gives me a minimum initially, namely at f of 3, 0, and a maximum when I get up there at 3, 2. So min 3, 0 will be, once again, plugging back in 9, and a max f of 3, 2, so that's 9 minus, let's see, 3, 2, 9 minus 3, 12, but then plus another 4, so it should get me 1. All right? 2 more to go. Let me consider L3. L3 I'll put over here because it's a bit more interesting. For L3, it's true that I've got y fixed at 2, but x gets to vary. So for L3, f of xy is going to be, is it x that varies? Yes, and y is stuck at 2. So x comma 2, this tells me I've got f of x2, which will be, let's see, x stays, so it's x squared minus 4x plus 4. All right, this isn't so simple as a parabola that's just increasing from 0 or a line that's just decreasing. This requires a small bit of calc analysis. You can do it really one of two ways. One of which is to realize that this is x minus 2 quantity squared in disguise. That tells me that I'll have min at 2, and then afterwards I'll have to test at maxes, the endpoints. So this says that I've got minimum at, we'll say, f of 2 comma 2, which will be, let's see, 2, 2, 2, 2, what is f of 2, 2 in this case? Hang on, do I agree? I agree. Cool, cool, cool. I'm back. Yeah, there we are. 4, 6, 2, 2, 4 minus 8 plus 4. Great, this will be, wow, 0. I then also need the endpoints, namely f of 2, or excuse me, 3, 2, which is 1, and f of 2, 0, 0, 2. Which will be, oh, let's see, 4. All right, so here's my min, and for the sake of L3, there's my max. Definitely need a bigger board. You didn't have to complete the square here. You could have done good old-fashioned Calc 1 analysis to this by finding, say, the derivative, f prime, which is 2x minus 4. Set that equal to 0. You'll get x is 2 for your critical value. Then make the number line 2. It will be decreasing and then increasing. So then you've got a minimum there. Then you need to do absolute extrema in the Calc 1 sense on this piece of a line by also checking the endpoints 0 and 3. It's a bit more involved than completing the square, but both work out great. Last line, line 4. 4. So for L4, what do I got? For L4, oh, this is nice. Y varies, but x remains at 0. So y varies, x is fixed at 0. So I lose all the terms but the 2y. This again is an increasing function of y. So increasing function of y. So I'm going to get this whole thing on the board because I'll have a minimum at 0, 0, which is 0, and I'll have a maximum at 0, 2, which is 0, 2, 0, 2, 0, 2, 0, 2, 4. Now, you'll notice there's a bit Squeeze myself in here. You'll notice there's a bit of redundancy in here because I calculated every corner of this twice. That's natural because you pick it up on each end, or you pick it up on the right endpoint of L1 and the left endpoint of L2. So, let me box it. Okay, so, what do I got? The largest value going is here at 9. And the smallest value is going to be here, not 0. And in fact, quite nicely, the 0 occurs in 2 places. So, to answer the question, I need just a bit of room. I've got minimum here, absolute min, at both 0, 0 and 2, 2. And the minimum is equal to f of 0, 0, or f of 2, 2, which will be 0. It's important to keep track of all the places you get the min, because a very askable question is not just what's the min value, but where does it occur? It occurs in 2 places here, one of which is definitely not an endpoint. And the max right there at 9.